For the last 12 lectures, we have been learning about mechanical systems and how to model mechanical systems that have linear constitutive laws relating mechanical variables, like position x and velocity v, to forces. Today we are going to start in a new area, chemical systems, where we will see that many of the lessons we learned from mechanical systems also apply in chemical diffusion. To understand the question we are going to try and answer, it is helpful to visualize a tank of water. This tank has length, depth, and width, but we are only going to consider the fluid in one dimension along its length. We will call this x. If there is a chemical in the fluid, the concentration C of that chemical can change as a function of position in the tank. That is, C can depend on x, so we will denote it by C of x. However, the concentration C of x is assumed not to vary with width or depth. We can plot C of x on top of the tank, so that the value of the curve represents the concentration of the chemical at the position x. For today, we are going to assume that the chemical is at equilibrium, meaning that the concentration throughout the tank is allowed to vary as a function of x, but is not allowed to vary with time. Also, we are going to assume that the volume V of the tank stays constant, because it makes things easier. Note that as a result of the equilibrium assumption, the amount of mass in any given volume V is constant. Also note that if I draw the tank again and mark in one position x1, another position x2, so that the distance between them is dx, and the total volume is equal to A times dx, then I get that the volume between them is V equals A dx, where A is the cross-sectional area in the width-depth plane of the tank, and dx is the difference between x1 and x2. If there are no reactions taking place and there is no accumulation of the chemical, for instance, the chemical is not precipitating, then conservation of mass implies that the amount of mass going into the volume V must be equal to the mass leaving V. We call the rate at which mass enters the volume the flux F, and in general F varies with x. We define the flux to be positive at a particular location, x1, if there is mass of the chemical diffusing from the left to the right at x1. Hence, conservation of mass implies that the flux F of x1 of the chemical into V at x1 must be the same as the flux F of x2 of the chemical out of V at x2. So if we have flux coming in, F of x1, and we have flux coming out, F of x2, we know that the flux at x1 must be equal to the flux at x2 because of conservation of mass. Now we ask the question, what drives the flux? What makes it be positive or negative? If C of x is a constant, then the concentration is the same everywhere, and we do not expect any flux of chemical. If I take this milk and pour it into the coffee, you'll see that it diffuses throughout the coffee. If the coffee is stirred and the milk is equally dispersed throughout the fluid, it would be very strange to have the milk start diffusing so that it was at a higher concentration in one place than another. Therefore, we don't expect f of x to depend on the absolute amount of chemical present. Said in terms we have used in mechanical systems before, we don't expect a constitutive law of the form f of x equals d times c of x, where d is some constant, because that would imply that positive concentration leads to positive flux of the chemical to the right in the diagram. Instead, if there is more chemical to the right, we expect the chemical to diffuse to the left. Alternatively, if there is more chemical to the left, we expect the chemical to diffuse to the right. The next simplest choice we can make is to propose that at any given x, say x1 or x2 in the figure, the propensity of the chemical to flow in the positive x direction is a function of the derivative dc of x dx rather than c of x. And, thinking back to mechanical systems, the simplest choice we could make is to make the constitutive law be linear with respect to the derivative of c. Lastly, what should the sign of the constant be? Well, if the concentration being higher to the right implies flux to the left, the constant must have a negative sign. These observations put together are called Fick's law, that states that the flux at any given point, f of x, is equal to minus d times the derivative of the concentration with respect to x times A, where A is the cross-sectional area, and it's in that term because flux is happening everywhere. It is worth noting that just like in mechanical systems, this linear relationship only occurs because we have a highly controlled environment. Fluid is still, it is probably very uniform, and the chemical being introduced is also uniform. If this was a natural system with all the environmental factors that could be introduced, a linear relationship between flux and the derivative of concentration with respect to position x probably cannot be expected. What should you remember from today? The key thing is that diffusion is driven by flux, and the simplest model of flux is called Fick's law.